So we're told europium exists in nature as two isotopes, EU-151 and EU-153. And we are given the masses of each of them. Okay. And we're given the average atomic mass. We're going to see a problem like this on your test where we give you the masses and ask you to solve for the relative abundance. Or we might give you other stuff and ask you to solve for the masses. Any kind of variation. So let's use this formula that we've been using in class. Mass of the first isotope times its percent abundance plus the mass of the second isotope times its relative abundance plus the mass of all the other isotopes, and then when you add them all up you get the atomic mass, which is a weighted average. In this type of problem we're only ever going to give you a scenario where there's two isotopes, because otherwise the math gets really hairy. Let's plug these in, plug these values in, do a little algebra. We have the mass of the first isotope, we have the mass of both of them. All right, so let's say EU-151 is the first isotope. So the mass of the first isotope is 150.9196, and percent is, we're looking for that, so we'll call that X, because it's asking us to calculate the relative abundance. Now we have the mass of the second isotope, that's EU-153, which is right over there, 152.9209 units times, since there's only two isotopes, we can say if one of them is X, the other one must be 100% minus X. 100% in decimal form is 1, so we'll do 1 minus X. And all of that's going to equal to the atomic mass, which is given to us, 151.96. Let's simplify this. This is just going to be 150.9196x plus, I'm going to distribute 152.9209 minus 152.9209x is equal to 1. The other side is 151.96. And right away, I mean, before you even got this far, you might have been like, well, if the average is 152, all right, and then the two isotopes are 151 and 153, then you're expecting a percent that's roughly in between, so 50-ish. Your answer should be close to 50-ish versus like 99%. All right, if that didn't make any sense at all, it's a way to check your work at the end, so maybe I should have just saved that for the end. Let's go back to this computation. Let's get rid of this guy right here. Subtract both sides. Is that a 2? Yeah, it's a 2. 209. Right, and do that to both sides. 152.9209. That gets rid of that. We're trying to isolate X on the left side. I'm just going to flip the order. Oh, excuse me. Oh man. 906. Borrow the 8. That's a 9. 0, 0. Okay. There's that. You can use your calculator if you want. I just reversed this because it's easier to subtract the bigger number from the smaller number, and I just stuck a negative sign at the end of that. So over here, that minus that, let's combine like terms. You know what? I'm just going to use my calculator. I'll be right back. Got my handy calculator. All right, so now let's do the 150.9196 minus 152.9209, and we're just combining the like terms here. The x's, negative 2.0013. All right, now let's isolate x, divide through by negative 2.0013. We need to get a positive number, right? For percent, can't have a negative percent. All right, that's gone. 9609 divided by 2.0013. Yep, it's about 50%, right? Now you can multiply that by 100 or move the decimal 2 times to get that number into a percent form. So I'll just do that now. 48.01. All right, let's see what that was. What do we call X? I think it was the EU-151. Yeah. So EU-151, isotope, europium 151 has a relative abundance of 48.01%, and then was it 153? I think it was. Is going to be 100% minus that, which is going to be percent.